Today we're going to be talking about a paper from the Google DeepMind team, and I have Isaac with me here today, who's going to be presenting the paper.
One of the things I've done so far in my time here is sort of read this paper, this Google DeepMind paper, which is sent in the announcements channel, and then sort of like think about like the implications, and it sort of like drove the direction of like one of the first experiments. But yeah, I guess we can start by diving into the high level topics of the paper. On a high level, what is this paper talking about? So we're looking at embedding models, specifically dense embedding models, and we're looking at how good they are at retrieval. So I guess to start out, the implicit assumptions we're using are that the dimension of the vector embedding is fixed. So I guess like high level, like we have like queries and documents in retrieval, right? And we want to convert them into vectors, and they all have to be the same dimension, because in order to determine how relevant a document is to a query, we will run cosine similarity or dot product on them. And a dot product close to 1 means that the document is very relevant to the query. And if it's closer to 0, then it's much less relevant. Or I guess usually there's a threshold point where you say it's relevant or not relevant. And what this paper is looking at is if we fix the dimension of the vector embedding, which we'll refer to as D, then how well can we represent like subsets of the documents, or how well can we represent sets of documents that are relevant to the query. So more specifically, what I mean is if we have a set of documents, if we have, let's just say queries, M queries, and N documents, for every single query, we want to rank the documents in terms of relevance based on their cosine similarity. So if we have like, so these are our queries and we have our documents. Just a very general thing that we want to be able to do in retrieval is we have our set of queries and our set of documents, and we want to use cosine similarity for every single individual query to compare how relevant documents are. So if we have a fixed query, it's an I right there, we want to compare these similarities. I'll just use S as the similarity function to compare relevance of the documents for QI. We obviously, like I said before, we need the queries and the documents to all have the same dimension of vector embedding so that like dot product is well defined. And for like practical reasons, or for like memory reasons or storage reasons, like you usually don't want D to be too massive. D being the dimension, not a document. Ideally, D to be not too large. However, usually if you think about like the geometric constraints of like a space, like RD, like the real numbers, RD. If D is pretty like smaller, you can imagine that there's less space in the geometry of like the vector space to have different vectors pointing in different directions, so that a given vector for a query can have like have a range of cosine similarities with all the different documents. And basically, like if the dimension is too small, like if you think of R2, which is just like a flat sheet of paper, the plane, there's only so many directions that these vectors can point in, where if I want like this query QI to have like a certain value with similarity value with D1, and then a certain something like that with D2, and then all the way up to D sub n, you like run out of space to optimize and place the documents in the right directions so that we have all of the similarity values that we desire. So it should be like geometrically intuitive that if D is kind of small, then you can't represent like all sorts of like tuples or combinations of these values that you want for relevance. And so I guess in terms of like what I mean by what we want, you can think of every query and document pair as being like denoted as relevant or irrelevant. So this is like a binary distinction. Do we, like, for example, I'll just start writing a matrix. So this is our queries, and then we have our documents, and then I want an entry to be 1 if like the document is deemed relevant to the query, and then I want an entry to be 0 if the document is not deemed relevant to the query. So this is like the general picture of like what we want to get when we have an embedding model. But what's really happening under the hood here is we don't just get this matrix out of nowhere. We're using the notion of cosine similarity, and so really what we have is our M queries, and then each of them is a vector of dimension D. So like this is the Q1 vector, and this is the last vector, QM. And then we're multiplying this by a matrix of the documents. And because of how matrix multiplication works, you take the columns of the documents, and then you get them with the rows of the query matrix. So, this is D. And so in this case, the documents are columns. So we have like first document, second document, all the way up to the last document. So this, when we multiply this matrix, you can check that the dimensions are m by n, and this is how we want to get this sort of ground truth matrix, which we call a QREL matrix, which is like, oh, for each query, like which documents are relevant to it. Now, obviously, when you multiply this matrix out, you won't get perfect 0, 1 entries. Like you only get that in an ideal case, right? But what we can sort of realistically hope for is like, if you multiply this out, and then let's call the product of this matrix, these two matrices B, and it's M by N. What if for each query I, so for each query I, like the similarity scores are just a row of the matrix. So this is M by N, and I'm just gonna call this row I. And we could hope that the set of values in this row can be partitioned so that every entry in row I that is relevant meaning the document is relevant to this query, has similarity greater than some threshold, just call it like lambda, and then everything that's irrelevant has similarity less than lambda. So this is like a reasonable goal to hope for. We want like relevant stuff to have higher constant similarity, and we want to be able to partition these into two groups. And so this is like the score matrix of a set of query and documents in an embedding. So like we have our queries, our documents, and then we have this embedding. This is a very reasonable thing to hope for. And we'd hope to have like this sort of model for every possible 0, 1 matrix. I'll just call this A. Like if we just look at like row I of this, we see like where all the ones are, and then we hope to have a score matrix B where the corresponding entries are all like larger than a certain threshold, and then all the other entries in that row are lower than that threshold. So this is like a very reasonable thing to hope for when we want to set up like our embedding model or like vector embeddings. But what this paper tells us is if D is too small relative to some parameters, well, namely like M, N, and then the ground truth matrix A, this is not always possible. So I guess I'll write that out again. If D is not large enough in terms of M, N, and parameters, so this notation is just like a 0, 1 matrix, M by N 0, 1 matrix. This is impossible. What this means is like, if we have a sufficient number of documents and queries and we don't want a massive like vector embedding dimension, then we can't get a score matrix that sort of has this nice partition property based on query for every single QREL matrix A, which is just like every single possible pairing of like relevant, irrelevant. And like on a high level, this is very bad, right? Because we want, ideally in an ideal world, like we would have a way to embed stuff that would just give us the relevance separation, relevance, irrelevance separation that we want. But this paper shows that it's impossible. And so this is like the sort of the theoretical part of the paper.